So in the previous week, we had been discussing regarding the background story behind this bending moment. And we had said that the origin lies in the sigma xx, the normal stress on any particular transverse section. So who can tell me, without drawing any figure or anything, just in your head, what is the origin or what could be the origin behind the shear force? Of course, it is going to be shear stresses because that is what this chapter is about. But what I want you to tell me is something a little bit more specific than that, meaning that suppose I have a beam like this, let's say a simply supported beam, and we have our very typical case of a point loading at the middle. And suppose I take a cut section here and I take the left part. So my free body diagram is going to look like this. Some R reaction force, some this P force applied externally, and these internal forces V, this internal force V and this bending moment M. My question is, what is the origin behind this V in terms of the shear stresses mentioned properly? What I mean by that is that this is our coordinate axis, X is like this, Y is like this, and Z, it is coming out of the plane of the screen. So you tell me, with the proper subscripts, what is the origin behind the V? Which shear stresses do you think would be responsible for the V?
2xy.
Sigma xy.
Sigma xy, very good. Okay, and I'm really glad that some of you have started saying things like this, that sigma xy and not tau xy, because you know, in certain places people make a big deal about that shear stress has to be tau, it cannot be written as sigma. It doesn't make any sense. Okay, it doesn't make any sense. Like if you write some other symbol also, it doesn't make any sense. I mean, it doesn't make any difference. All right, so what we'll do is we will consider a cross section, the kind of cross section which we had dealt with in our previous week also, meaning a cross section right symmetry. So let's consider something like this, like a trapezoid. So this is our cross section, and let's say this is our beam. Okay. And what we are saying is that we have this force V appearing here and this bending moment M. The origin behind this V, that is with sigma xy or tau xy. Now, for the sake of clarity, I will just remove this M. Okay, otherwise it's going to be a completely cluttered picture. So we understand that this is our X, this here is our Y, and Z is in this fashion. Okay. Now, the sigma xx is like this. This is our sigma xx, and our sigma xy or tau xy, because in your textbook it is written as tau xy. I'll continue to write like tau xy, but doesn't make any difference. So our tau xy will look like this. Okay. Please, whenever you are encountering the shear stress, please make it a point to note that the direction of the arrow in which we are depicting this, it is we are being faithful to the positivity convention which we had agreed upon previously. So we are drawing the shear stress on a plane on which the outward normal is along the positive x direction. So in order to maintain the positivity convention, we have to consider the direction of the shear stresses along the positive y direction. So the first subscript here, x, is along the positive x direction, along which the unit outward normal is. And the second subscript, it denotes the positive direction of the shear stress, this along the positive y. Now, just like before, we had said in the previous chapter, we had said that y times sigma xx dy. So sigma xx dy is the elemental force acting on a little area of element on the cross section. This y is the moment arm, and when you take this moment and add it up over the all such moment contributions over the entire cross section, the thing that you will get will be equal to minus m. This was from the previous chapter. Okay, so all this I'm writing is in the rough column, just to remind you of what we discussed in the previous chapter, in the previous chapters. Now you tell me, taking an inspiration from this, what should be the relation between tau xy and v? This is the heart and soul of what we are going to discuss subsequently. Tell me. So relation, just like there is a relation between sigma xx and m here, by integrating over the entire area, what do you think should be the relation between tau xy and v?
So tau xy into the area would be equal to v.
Very good. It is as simple as that. Tau xy times the elemental area gives me an elemental force in the vertically upward direction, that is along the positive y direction. And if I integrate that over the entire area, I should be able to obtain the entire shear force that is acting over this cross section. But the entire shear force acting over this cross section is nothing but this v, which we have taken downward. So the only thing that we have to adjust for is that it should be like this. That's it. Okay. Furthermore, please do not think that we are carrying out some kind of a force balance here. Okay, this is not a force balance. This is the background behind the V. Just like this M, the background behind this M was this, so also the background behind this V is this thing on the left hand side. It is not, we are not carrying out a force balance. You are only supposed to do a force balance when you take a cut section. Okay, maybe two cut sections, take out a little chunk of the beam and then write the force balance for that. We are not doing that. We are only locating ourselves or looking at this particular cross section. That's it. Okay, these small things must be absolutely clear in your head. Now we are at the same situation. We are in the same situation that we were previously. In the previous chapter, we were stuck here. In this chapter, we are also stuck here. After this, whatever we have to say, we have to bring in something extra. So the thing that we brought in extra in the previous chapter at this point, after this, was that we started looking at the deformations. And by looking at the deformations, we were able to say some things regarding the strains. And then using the Hooke's law, we were able to connect the stresses with the strains, and that's how we brought everything close together. Okay, we closed everything. Now, you might be tempted to think that here also we have to do something similar. Ideally, theoretically, yes, we have to do something similar. We have to bring in somehow the deformations of the beam in order to write anything extra regarding this. But the practical truth is that as far as the shear stresses are concerned, or the shearing action is concerned, it is not very easy to write down directly the shearing strains. It is much more difficult to visualize. So what is usually done is that an alternative route is taken to go further. Okay, that alternative route can be taken because we have already done this previous chapter. Okay, so it is as if we are building a large brick wall where we have laid down the groundwork earlier in the earlier chapters, and now we are building the higher levels of this brick wall. Okay, it is as if in our learning also we are doing some kind of an engineering. We are step by step building up our concepts. Okay, so every time we don't have to start from scratch, looking at the deformations in a very basic fashion. We don't have to do that. There is an indirect way of going forward, and which is much easier, and will appeal to that. So what we do is the following. Let me go to the next page, and I'll do a force balance, something which is very comfortable for all of you. So what I'll do is I'll take out a little slice of the beam. So I've taken a little slice of the beam. So what I'm basically doing is that I'm taking a cut section here. Okay, I'm taking a cut section here. Okay, slicing off that thing and taking out the this chunk. Okay, so now what is going to happen is that let me draw this surface at the back. On this back surface, I'm going to see a certain distribution of the normal stress. Something like that. So this is sigma xx. Now, on this surface, on this front surface, I'm going to experience sigma xx, but with a slight increment. Furthermore, you note that the thickness of this piece of the beam that you have taken out, that is delta x. For even further on you, okay, I'll come to that later. For now, you just think that this is sigma xx plus delta sigma x, and on the back surface, it is sigma xx. And I want to do a force balance. You also note that this piece that I have taken out. So what I mean to say is that this bottom surface, okay, this bottom surface, this bottom line that you are seeing here, this bottom line, if you compare with the previous thing, it is not this bottom line. Rather, what I have done is I have taken out, I have cut this at this location maybe. Okay, please do not think that I am cutting it at the mid height or anything. It is at some arbitrary distance from the top surface. Okay, it is some arbitrary distance from the top surface, and I'm taking out this portion. I'm considering this portion, this hatched portion. So this bottom surface here, it corresponds to this bottom, this one, this line. I'm just drawing it in an exaggerated fashion. Now you see, along the positive x direction, I have a force associated with sigma xx plus delta sigma xx. And on the back surface, I have a force associated with sigma xx. The area of this front surface is equal to the area of this back surface because we are considering a prismatic beam. A prismatic beam is a beam which has a uniform cross section all along its longitudinal axis. So this is such a beam. There is no difference in the area in the front surface and the area in the back surface. Area is same. Stresses are different on the front surface and the back surface. meaning that there is a force imbalance if we just consider the forces associated with this stress and with this stress along the x direction. Which means what? There must be something else which must be balancing this force. Where is that force? Or what is the force that is balancing this mismatch? Who can tell me? Take a guess. I hope all of you have understood my question. There is a force mismatch if you consider the stresses associated with this front surface and the stresses associated with the back surface. And this mismatch is along the x direction.
Shear forces are from the bottom surface.
Shear forces on the bottom surface. That is what is going to balance out this mismatch between the force in the front and the back. So let me write this thing out explicitly. It will be more clear to you. So sigma xx plus delta sigma xx integrated over this area dA dash. So this A dash, it represents this area which is not the entire cross-sectional area of the beam, rather it corresponds to the arbitrary cut that I have taken at a certain height from the top. So what I mean to say is that this hatched portion, that area is A dash. So this integration is over that A dash minus sigma xx, again the same area. This is the force mismatch. This force mismatch is balanced by the forces which are there on the bottom flat surface. So let me highlight to you that this is the bottom surface we are talking about. This rectangular thing at the bottom, on that surface you are going to have some kind of shear force. That shear force will be associated with some shear stresses. Tell me, what should be the direction of that shear stress? What should be the direction of that shear stress?
Sigma yx.
Sigma yx.
It should be sigma yx. Okay, but which direction my arrow should be pointing?
Towards negative x-axis.
Very good. Towards the negative x-axis. Very good, very good. So if I look at it from this side, okay, you understand that the z-axis is like this. What I mean to say is that suppose I look into this picture by looking into the z direction, then my diagram will look like this, just like a rectangle, and this bottom surface will just be projected in the form of this horizontal line at the bottom. And on this bottom surface, let us not forget that now in this particular view, our x-axis is like this. My writing app crashed. Sorry. I hope something is salvaged. Just a second. It is okay. Yeah, everything is fine. I'll quickly save this thing. Okay, we are back in business. So this is our x-axis. This is our y-axis. Now we are talking about this bottom surface because we are talking about this bottom rectangle. So there, the unit outward normal is along the negative y-axis, which means in order to maintain the positivity convention, if I want to write this tau, it is something like this, that I have for the first subscript, I have minus y, and the second one it is minus x. Minus x means the arrow should be pointing like this. Okay, so this is the direction of my shear stress, tau yx. So this force balance will be in this form, tau yx times, what is the area now? Now you cannot write this thing without actually knowing what is the breadth of this. So as per the notation used in our textbook, Beer and Johnson, what we'll do is we'll take this distance to be t. This thickness or this breadth along the bottom surface to be t. So this area is t times delta x. All right, t times delta x is the area of this bottom rectangle. Please note that the direction of the force of this thing, it is along the negative x direction. This force is also along the negative x direction. So it makes sense that this here is on the minus sign. If you take it to the right hand side, it will be positive sign. So this and this are in the same direction. This is in the opposite direction. So everything is all right. So in the next step, we can simplify this a little bit by noting that this sigma xx dA dash integration a dash will be cancelling out with this. So we'll be left with just this thing, delta sigma xx dA dash integrated over the entire area a dash, and this is going to be equal to tau yx t delta x. Now we are just going to swap the two sides. Tau yx will keep the t on the left hand side, but we'll take the delta x inside this integration. It doesn't make any difference because delta x has nothing to do with this particular area. So it's almost like a constant with respect to this integration. So this is delta sigma xx divided by delta x dA dash. Now what we are going to do is consider the limit that delta x tends to 0. Basically, we are going to take this back surface to be very, very close to this front surface. That is completely in our hand. We can do that. So in that limit, what we are going to do, what we're going to end up with is this thing, that this delta sigma xx divided by delta x, it will turn to this form of a differentiation. Now you can probably understand why we are taking this kind of an alternative approach towards obtaining an expression for this tau yx. The reason, if you have not already realized it, is that from our earlier chapter, our hand an expression for this sigma xx in terms of the external things. What is that? So the sigma xx, the formula for it was minus my by I. Was it not? Minus my by I. So let's check this thing. Let's go to the next page.
Sir,
Yes.
hello, sir.
Yes.
Why we not consider the tau xy of upper surface, sir?
You are not audible. Hello.
Hello. Now it's fine, sir, or not, sir?
Yes. Now I can hear you. Tell me.
Sir, why we not consider the tau xy of upper surface? We only consider the lower surface of tau xy, sir.
This one, this top surface.
Yes, sir.
Yeah, this top surface is actually free from stresses because it is the actual top surface of the beam. So you see that top surface is the actual top surface of the beam, and there are no direct shear forces acting on that. Okay, it is completely free from any shear stresses, neither in this direction along the z direction nor along this x direction. The only force that it may be experiencing is in this transverse direction, like we studied during our bending moment in our bending moment chapter. Okay, there may be some loading on this thing in the vertically downward direction, vertically upward direction, but there are no forces along this surface. Okay, because there are no forces along that surface, there are no shear stresses also on the top surface. So the top surface is actually in physical reality free from any shear stress.
But sir, in questions we also not seen the any forces on the lower surface, sir.
Say that again.
Sir, in the question we also not see the forces on the any external shear force on the lower surface, sir.
This is not the lower. So if we take the actual lower surface, that lower surface is also going to be free from shear, and we are going to see that when we finally end up with the expression, we'll see that the actual lower surface is also going to be free from shear. But the lower surface that you are seeing here, this lower surface is not this lower surface. It is this one within the beam. So within the beam, there are going to be shear stresses. Okay. Inside the beam, there are going to be shear stresses, okay, but the top surface and the actual bottom surface, they are going to be free from shear. That's the thing. All right. So we end up with this thing ddx of sigma xx, and sigma xx is y is what? Minus my by I dA dash. Now you see this I is the second moment of area or the area moment of inertia, and because it is a prismatic beam, completely uniform cross section all along the length, and the length is along the x direction, the I is not going to have any variation with x. The M can have a variation with x, certainly. Why? Because you have already seen when drawing the bending moment diagram that the M has a variation with x. It can vary along the length. Y is a completely independent coordinate variable from this other coordinate variable x. So certainly your dy dx is going to be equal to 0. So from within this expression, minus my by I, the M can be taken out of this differentiation. The I can be taken out of this differentiation. The y can be taken out of this differentiation, sorry, and the I can be taken out of this. M cannot be taken out. M has to stay within it. So we'll be left with this thing minus so it's something like this, a dash y by I. In fact, this I can also be taken out of this integration, but for now we keep it inside. It's like this. Now you tell me this dm dx thing, what is it? You all know.
V.
Exactly. This dm dx, as per our previous chapter, it is nothing but V. So this thing is V y by I dA dash. Now you see this integration is over the entire cross section. The V is just a constant value at a particular cross section. It does not have, this V does not have any variation over the cross section. Similarly, the second moment of area, it has a unique value corresponding to a particular cross section. It is not varying itself over the cross section. So both this V and the I can be taken out of this integration. That's what we'll do. So we are left with this. So overall, what we are getting is tau yx. Therefore, tau yx is going to be equal to minus V by IT, and this particular integration that is depicted by Q. Q is equal to integration y dA dash. This is referred to as the, you already know this, tell me what it is.
First area moment of inertia.
It is the first, yeah, it is the first moment of area. But there is something special going on with this first moment of area. It is not the first moment of area of the entire cross section, mind you, because you note that we are not talking about the entire area of the whole cross section. We are talking about the first moment of area which is associated with this horizontal cut. Okay, at the level where we are taking this horizontal cut. Okay, so for this hashed portion, that is for which we are taking the first moment of area. It is not for the entire cross section. Okay, first moment of area of the part of the cross section under consideration. This is extremely important. So in calculations, this is where people can make a severe conceptual mistake. So this is your expression. Okay, now if you compare with your textbook, you will see that there is a difference in sign. Okay, with this thing, this tau yx is equal to minus bq by it. You will see that there is a difference in the sign. This minus sign, it is not there. The reason is that I think while doing their derivation in the textbook, they have not taken this sigma xx is equal to minus my by I. Okay, but earlier we have seen that it is minus my by I. So I have directly put down that thing in order to be completely faithful to our previous chapters. So we'll see the implications of this formula in a bit. Now, there are certain very important things. See, as far as the basics of this chapter is there, it's done. Okay, this is the formula. This is what is referred to as the shear stress formula. This is the shear stress formula. Okay, and we are done. But saying done is not enough. All right, because there are a number of small nuts and bolts details which we have to deal with, which we have to be extremely careful about. And as you have seen by now, the devil is always in the details. Okay, so you have to really understand where this is applicable, where it is not applicable, and wherever it is applicable, how do you actually apply it? How do you go about doing these things? And there are certain limitations also to finding these things. So instead of talking about those things in a very theoretical, abstract fashion, I think it will be best if I keep on illustrating those small points by actually finding out expressions corresponding to some very common cross sections. So what I'll do is, first of all, take the easiest of cross sections, meaning a rectangular cross section, and then we'll see what is the meaning of all these things. So let me quickly go to the next slide. Take a rectangular cross section like this. Where this is the breadth B, this is the height, for this rectangular cross section. You all know that the neutral axis would be passing through the centroid, and that centroid is actually at the level of h by 2 at the midpoint. So this is the neutral axis. And we are going to locate the origin of our coordinate axis also here. So our y will be something like this. This is our y. And like before, this is our x. Now, we are going to consider the part of the cross section from the top surface up to this much height. So we are going to consider this hatched portion, meaning that we are going to consider the shear stresses on this bottom surface. Now, till now, none of you have asked me one simple question. Probably you have figured it out, that's why you did not ask me. But let me just quickly go back to this previous thing and ask you. See, our original intention, if you go back here, was to find out this tau xy. But I have ended up with an expression for tau yx. What is going on? So why am I happy after getting this tau yx? Why am I not making any extra effort to find out tau xy? Yes, exactly. So see, that is the entire motivation of this alternative approach of finding out the shear stress. Our original motivation, our original plan was to talk about the shear stresses which is on this YZ plane, or on a plane which is parallel to the YZ plane. But we have ended up finding out the shear stress not on this plane, rather on this horizontal plane. That horizontal plane is parallel to the XZ plane. You see, in this diagram, the tau yx that we have found out, that is lying on which plane? That is lying on a plane which is parallel to the XZ plane, because this is that plane. But the truth is that the moment you find out this tau yx, the tau xy, which is present here on this right hand side, this is the tau xy, it is automatically found out because tau xy is actually equal to tau yx. That is the whole point of this thing. Okay, so separately you don't have to do any extra effort to find out the tau xy. Tau xy is equal to tau yx is equal to minus vq by it. So this also gives us a very important physical understanding. It is not just a mathematical convenience, it is also an important physical insight into the situation, that when we are talking about the shear forces in this transverse section as a result of loadings that are taking place on this top surface, simultaneously on these horizontal planes also, okay, on these horizontal planes also, there are certain shear forces being developed. Okay, there are certain shear forces which are being developed on these horizontal faces also, having a magnitude equal to these shear stresses. So those shear stresses on those planes, on those horizontal planes, they're actually equal to the shear stresses on these vertical things. It's a very important insight. Now, let us get back to our rectangle. So we are interested in finding out the shear stresses on this particular cross section, and we are going to appeal to this equality, that effectively what you would be doing is to find out finding out the shear stresses on this horizontal plane. So this is the actual top surface of the beam. This one, we are not talking about that top surface, that horizontal plane. Rather, we are talking about this one. Okay. So on that one, you'll find out some tau yx. All right. How do you find out? You see, in this formula, your V is known, your T is given. What is the value of T for this simple rectangular cross section? Tell me.
B.
It is simply B. So for this problem, it is the easiest thing to identify that in our formula, this T is equal to B. What is our I? I is the second moment of area with respect to the neutral axis. So what is the value of this I? You have done this number of times.
1 by 12 BW cube.
B H cube. Not W, okay, that is H.
Okay, sorry.
No, it's my handwriting, that's bad. This is H. Okay, 1 by 12 BH cube. The total height is H. Okay. T is known, I is known. For a particular cross section, there will be some V, which we'll be able to find out from the bending moment and the shear force diagram. So V is also known. So the only brain work that you have to do is for finding out this Q. Okay, so Q is the thing which you have to find out. Tell me what is Q? Actually, this is a one-line thing. All right, what is the Q? Q is the first moment of area of this hatched portion. All right, so first moment of area means we have to first write down the area. What is the area of that? It is simply B into how much? So you take this much distance. Okay, what I'm saying is that you take this much distance from the neutral axis to be Y. Let me depict it properly. Or maybe I draw a separate diagram. Slightly larger, it will be clearer. So this much distance is Y. This height here is H by 2. Now you tell me.
Sir,
3 times of H by 2 minus Y.
Yeah.
So B by 2 into A square by 4 minus Y square.
No, tell me slowly. So this is, what is the height of this? This is H by 2 minus Y. This is the height, B into H by 2 minus Y. What is the moment arm? The moment arm for this area, that will be calculated from the neutral axis to the centroid of that particular cross section. That particular cross section means that particular area under consideration, this yellow hatched area. The centroid of that will be lying somewhere here. This is the point. What is the distance of that point from the neutral axis? It is going to be Y plus
half of H by 2 minus Y.
Half of H by 2 minus Y. Very good. This is the first moment of area, Q. Okay, and you can simplify this, but effectively this is your thing. Okay, so if you just simplify this thing and put it back in this expression, you are going to get your value for the tau yx. I'm noticing that I've run out of time for this period, so we'll continue with our discussions on Thursday. All the very best for your test on Wednesday. Prepare well. All right, so we'll meet on Thursday.
Sir, for this thing, can't we direct means integrate the thing from Y to H by 2, putting the limits?
I will come to that. I will come to that. Okay, because in certain types of cross sections, you might actually have to do that integration manually. This kind of a simple calculation will not be possible. Okay.
Okay, sir.
Yeah. Okay, sir. All right. Thank you guys very much. Please go to your next class.
Thank you, sir.
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 Thank you.
Thank you, sir.
Yeah.